Hello, world, and welcome to Code or Not to Code. I'm Millie Eva, and as always, I'm super happy to be here today. And I'm here with Stefan. How are you doing?
I'm doing great. It feels, I think we're getting back into our regular schedule, and it's amazing.
Yes, it does feel good to be back on a regular basis. It's true, and yeah, we already in the preparation we did a lot better than we did like 2 weeks ago. So, hello, Eric. Thank you so much for being here today. Welcome to all of our regulars, but also everybody who's new to the show. If you haven't seen us before, the two of us usually meet every other week and code together and learn together and laugh together and just take everyone along the ride. And yeah, we have a really special episode planned for you today. But before we go into that, please don't forget to, like and subscribe. You know the drill. This is a stream. That's what we do. So please, if you want to reach out, any of our social media channels, they are listed below. So if you have any questions, comments, suggestions for upcoming content, or just want to reach out and say hi, it absolutely makes our day, a week, if I'm being completely honest. And since we sort of semi-regular, we don't always stream on the same day and stuff like that. It's a really good way to sort of like keep in touch with us and keep in the loop with our upcoming shows as well. All right. So Stefan, what are we doing today?
Before we jump into the topic, saying goodbye.
Before we say goodbye.
saying goodbye to everybody. Yeah. Hello. Hello, YCC. And hello, Ruben Woodcraft. We have met Ruben in Tekorama.
Did we? Oh my goodness. Thank you so much for joining this stream. Wow. That's so cool. Tekorama was really awesome.
And well, I guess we did some shenanigans and some patterns in at our presentations, and we called always a bunch of methods. So this episode, we are promising. For how long are we promising benchmarking now?
Oh goodness. Quite a
while, right? We're not building up to it, so this will be now a full episode of a teaser for the next episode, because what we're gonna start with is how to building a bit of helper library that facilitates benchmarking Rosling components like analyzers and generators. But when we now take a peek at a generator, in a previous episode we rewrote one. Well, there is an interface. And this interface declares a method. And when we now implement this interface on a type, we need to implement this either explicitly or implicitly. So I have here an instance method and also a static method. Now, if we were to call these methods, there is like different ways of calling it. So there is, we either can call this initialize method directly via the actual type or indirectly via the interface that this type is implementing then. We can also invoke static methods. And what we recently do a lot, not only taking a look at the lowered C# code to get rid of the syntactic sugar, but also at the EIL code that I guess we partially understand. Maybe we understand 0.5% or something.
Yeah, kind of.
But we practiced our eye in our pattern talk to detect a lot of patterns. So when we call instance methods, we see that there is some instance calls, and there's also a call word, something virtual. However, if we invoke a static method, well, it's just a call. There is no call word. Another interesting thing is, what about properties? I'm having here a property. And where's the example? We just set and get the property. Taking a peek at the EIL code, these are also calls. And they actually look like get and set methods. So properties, when we deal with properties, they are also just calling methods. We are here in a top level statements. So that's just a program CS without the main method declared. But again, now, well, if we take a look at the low-level C# code, we see there is also the main method. So there is methods everywhere, and that totally did not prepare the Toy Story Me methods everywhere. And so as a build-up because then with benchmarking, we will run a lot of methods a lot of times and then calculate statistics to see how fast they were. Then you can make some improvements to that method and then see if now the next benchmark one that runs a lot of times because there is JIT, there is tiered compilation, so a method may be called more efficiently in subsequent runs to get some statistics of the performance out of the methods. So there is methods just everywhere, and it's the foundation of everything. And I just realized that I have absolutely no idea of how a method works under the hood, although they are absolutely everywhere.
Yeah, they are absolutely everywhere. But unfortunately, Stefan, I also don't know too much about them.
Damn it.
But
Damn it.
I know. But don't worry, everybody. We did bring in an expert who will help us today answering all of those questions, all of our questions, all of your questions, and probably some more. He's an absolutely incredible human being, kind of superhuman sometimes. He's a Microsoft MVP. He's a principal engineer at JetBrains. And you've also met him before, our regulars have, because he was on the show, because he's also co-author of Pro.NET Memory Management, the second edition. Do you have it still on your desk? Yes. Over there it is.
Oh, no, it's just below the name. Yeah, but it's here.
No, but it's there.
Yeah, the robot.
Just next to the Tekorama figure. But yeah, so you might remember him because he built his own, he's built a garbage collector in C#. He's got his own blog. He's honestly incredible. Please welcome Kevin Gosse.
Well, no pressure after this presentation.
No, you'll be fine, trust me.
Yeah, hello. Thank you for having me here today. Yeah, very happy to be there.
Thank you so much. How have you been since we last saw you? Because, I mean, we sort of took a little bit of a break because we went to a couple of conferences, but you were busy as well, weren't you?
Yeah, so I in the meantime, I did a talk at a conference too, at Update conference in Krakow, about methods, and so that's what we're going to talk about today. And I also changed company. I left Datadog and joined JetBrains, in which I'm working on improving the performance of ReSharper. So yeah, that's a lot of work. And so the past months has been a bit overwhelming.
Yeah, I bet. Big changes and conferences. And I guess for me, it was my first time ever on a conference. But I guess, you know, like it was probably not your first time, but it's always like, I guess, a big adventure and, you know, a lot of excitement, isn't it? Or does it get better?
Yeah, I really love that. And I hope that this is only your first time of a long series of talk. Do you have another one planned yet, or?
Well, we have to come up with some topics, but yeah. Well, it was definitely a really cool experience. Yeah, both conferences were really, really incredible, and yeah, it's just so nice to kind of. I mean, it's always lovely to meet the community in like, you know, meetups or like through the stream. But when you have, you know, so many people from the community right there, like physically there, and you can actually you know, interact and reach out, it's just it's really good vibes and a really buzzing place, I guess, buzzing with ideas and excitement. So yeah, it was definitely a good experience.
Exactly. Yeah, I love it.
All right, I guess what my question is, because we were talking about coming up with topics for conferences, and you mentioned that you had at a conference a talk about methods. So I was wondering, like, what made you a master of methods? How did you stumble across this topic? Was it through your book or your blog or just life?
So how did it start? Basically, it started with a pet project, and actually I made the garbage collector is part of it. I made a series of projects where I tried to use C# at places where it wasn't intended to be. And to make it work, I had to learn a lot about native interrupt. And that's when I discovered that a lot of things didn't work so the way I expected them to. Or really simply questions that I never asked myself. And then when I learned this answer, I was a bit mind blown. And so I decided to share this knowledge. Because there are a lot of things that we think we know, and then when we start thinking about it, we realize that our mental model of them just doesn't work. So to take a concrete example that will be a teaser for later, I think most people know that when you call a function, you are going to store arguments in registers. But then if you have an object, you're going to store the address of the object. If you have a long, you're going to store the value in the register. But then if you have a struct that is, I don't know, 500 bytes, it doesn't fit in a register. And yet you are supposed to pass it by value. So how does it work? That's a kind of question. Before you start thinking about it, you don't realize that there's something missing in the picture.
Yeah. Interesting.
Is this kind of related? Yeah. So because every object has like the method table, but so this overhead of a method table, but overhead allocates memory for the method table or a pointer to the method table, but a struct doesn't have that. Is this kind of related?
No, it's not related.
No. Okay. That I don't even understand what I don't understand.
Yes, indeed, that is the first step, isn't it? Understanding what you don't understand. But so we're like, I guess let's start at the basics. Like, what is a function?
So you can share my screen. So that is a function.
Thank you.
All right. I think we're done for today. I'm having a bit of a problem with my setups. Give me just 1 second. There we go. All right. Yes. So this is a function. So a function is a reusable bit of code that you can call from pretty much anywhere. Actually, let's show it from the assembly level. And so if I write a function and then I call it, colon. And then I call, and here nothing happens.
We can't see. We only see.
Thank you. Right.
This is I guess some overlay, right?
Yeah. So I guess I'm going to present the whole screen, and we won't have this problem anymore. Let's see. So present, share screen. There we go.
Can I bring it on the stage?
Yes, please. All right. Yeah, so as I was saying, so using sharplab that you might already know, you can type C# code and you can decompile it into IL or assembly code, or even into C# if you want to see the low-level structs. And so here nothing happens because my function is getting in line, because the compiler is smart enough to realize that the function is empty, and so compilation it removes it. And so we can simply decorate it with sharplab used to be great, but it's kind of broken lately.
Yeah.
The auto-completion keeps deleting everything you write.
Yep.
Seems to work.
All right. Okay, so here, that's another case interesting in that the compiler realized that because color is trivial, it just compiles into a jump instruction. But if I do this, we'll get there eventually. So, and return value is 1. That's another.
Oh yeah, there we go with the deletion. Would you mind zooming in just a little bit more?
Yeah, there we go.
Woohoo.
Yeah.
Oh, wow. So there's now a lot more, because so previously when we called an empty method, this method wasn't called, we just had ret. I assume that's return. So the caller was called, but nothing happened because M was inlined, which again also just was a return. So we have a kind of return. Now that
if I remove the no inlining, then we see in caller that we're not calling M at all because the compiler copies the body of M inside of caller. And
so
actually,
is this was inlining it? I thought inlining actually was copying the content of the method into, but it's just jumping then to that without a method invocation. Or am I missing there something?
I'm not sure I understand the nuance in what you said. So inlining is copying the body of this method inside of this one. But here it's actually another interesting. I wasn't planning to go there yet, but since we are here. So in my base example, we have the caller method. So first we are setting what is called a stack frame. We can go back to this later. Then we call the instruction with a call instruction. What is call doing? Call is a shorthand for pushing the current address on the stack and then jumping to the target address. So this is two instructions in one. And then inside of the function, what we do is we move the value 5. Here we return 5. So we move the value 5 into EAX, which is the register used for the return value. And then we call the ret instruction, and the ret will pop the return address from the stack and jump to it. So ret and call are meant to work in pair. And then when we return, we increment the value, that's the +1 here, and we return. And if I remove the no inlining attribute, so I let the compiler inline it, we see something interesting in that. So because the method has been inline, the method call has been removed. But then also, what the JIT did is copying this into this, and then it realized that 5 + 1 is a constant, and so it directly computed the result, which is an optimization known as constant folding. So yeah, I wasn't planning to get there just yet, but one of the benefits of inlining that we tend to think about is that we remove a method call, which is true. But another benefit is that by grouping the code of multiple functions in one, we allow the JIT to do optimization that it wouldn't be allowed to see otherwise.
Oh yeah, so my code actually looks totally different without. Now I understand that without debugging symbols of a release version of a code that gets highly optimized, yeah, we can't debug this with our original source code because it doesn't look like our original source code anymore, does it?
Exactly. That is true. That is a very good point. So here we had 2 lines, so you could expect that you could set a breakpoint here, but it has been transformed into a single line. So when you step into it with a debugger, it's going to jump all the lines.
Now we have a comment from chat mentioning AOT. Now, is this related to ahead of time compilation?
What AOT is going to do is exactly this, but it's going to do it at compilation time, whereas the JIT is doing that the first time you call a method. And it has some pros and cons. When you are using native AOT, there are 2 major differences. The first one is that you have the JIT compiler, everything is compiled at compilation time. And also you have a finite set of types. Basically, in .NET application, at any time you can load an assembly, which will add other types to your process. And because of that, there is a bunch of optimizations that are not possible. for instance, let's say you have an interface. Even if you don't use it, the compiler can't remove it because at runtime you might load another assembly which requires that interface, and so you can't remove it. Whereas in native AOT, because you can't load an assembly, and so you know all the types that you are going to use at runtime, and so the compiler can aggressively remove them.
Yes. Oh, is this? I once saw a blog post mentioning about the performance automations of sealed, so that the compiler or the runtime can make optimizations. I guess, is this also related, or is this something that is more for the JIT compiler, not for the AOT compiler to optimize on?
So basically, yes, that's something that was added fairly recently. I think .NET 7, maybe .NET 6. Before that, the sealed keyword made no difference at all in .NET.
Oh, it was just for the C# code to basically I make it's more of a contract.
Yeah, exactly.
From a design perspective, but it didn't have any runtime influence. But now with later versions, and now also the runtime is inspecting the. I see.
Exactly. Now they have started implementing optimization for the JIT that take advantage of the sealed keyword. And so basically the kind of optimization is devirtualization. So we can go back to this later, but doing a virtual calls is slightly more involved than doing a normal call. And so if you have a virtual method on a class, then it has to be a virtual call. But if you decorate it with a sealed keyword, then the JIT compiler knows that you are never going to override it, and therefore it can convert it to a concrete call. And in native AOT, you don't need the sealed keyword because the compiler can deduce it because it already knows all the type of compilation time.
Yes, I see. And then now, okay, I think I also tune in sometimes to the .NET API reviews. They weekly or sometimes bi-weekly review the public API surface that comes for the next version of .NET. And they always discuss breaking changes. And at some point discussed that removing the sealed keyword is a binary breaking, well, is some breaking change. Is it actually because if the code has compiled with the sealed to don't assume there is more derivatives, but if I remove the sealed and then don't recompile, just swap in the assembly, now there could be a more derived type. So. Is this related, or am I again mixing something up?
I don't think that those optimizations, the optimization that I described happened at runtime by the JIT compiler, not when compiling to IL. So I don't actually know what breaking change you introduce by adding the sealed keyword. So that would be interesting to look into it.
I may also totally mix something up. This is actually very likely.
No, I mean that's possible. But that's really interesting.
Hi, Stuart. Thanks so much for joining.
Now you mentioned EAX. That's always the register for the return value.
On Windows, is that on Linux too? I wonder. On Windows, it is for sure. I don't know if SharpLab is using Windows or Linux. Basically, if I add arguments to my method, let's add 5 of them. My computer. Right, and then I call it. There we go. Yeah, and I it went back to inline. Okay. And I need to make this static. Sorry. Okay. Yes. So that's Windows. That's Windows. So they use Windows.
How do you see that? I don't see.
Exactly.
No
so the way you give arguments to a method, a function is defined by what we call the calling convention, and there are many calling conventions available. And the calling convention used on Windows x64 say that when calling a method, you give your arguments in order, you store your arguments in order in the RCX register, RDX, R8, R9. So I'm saying RCX and you see ECX. So that's because so RCX is a full 64-bit register, and ECX is the first or the last, I don't remember, 32-bit part of that register. It's because x64 is compatible with x86. You can run 32-bit program on your 64-bit application. And here int is 32-bit. And so it's using the 32-bit denomination of the register. But if I convert to long, it will become RCX. Maybe. Why is nothing happening? I don't understand why.
Is anything?
I don't know what's going on.
Is it reloading? Maybe if you try to make a compiler error, maybe it hasn't reloaded or something.
Yeah.
Oh, now we get the loading.
Oh. Yeah, I don't understand. Is it because... Maybe it's smart enough to know that I'm giving...
oh, it's optimizing.
In value.
So if you do like, if instead pass like long.max value, so that it can't, so that there are no constants anymore.
I have an error outside of the screen. There you go. Yeah, there we go. So yes. RCX, RDX, R8.
Yes. Okay. So the JIT compiler was smart enough. Okay, although the method took a long, it understood that it was constant. It was received an integer constant or just a byte constant that fits into a 33 and it's 64, and it was just optimizing it.
Yeah, I'm actually curious. It might not always be possible. I think it was possible because the method was trivial. But I need to check my assembly. But I think if you do move ECX, then you store 32-bit in your 64-bit register, but you don't clear the other 32 bits, which would be a problem. And so I think in that case, it knew that there was nothing in the register previously, and so the register was already zeroed. But I assume that if I had some code there, then it couldn't do that. But I need to check. Here I'm a bit out of my out of my comfort zone, to be honest.
I guess there's a lot of ad hoc questions, such as not a question but a statement. It doesn't use ASM though. Actually, what does this mean?
I think it's what was the conversation about?
I think if SharpLab is running on Windows or Linux.
Yeah, they both use ASM, so I don't know.
I may have also again mixed something up, very likely.
Yeah, and so the calling convention said that the first 4 arguments are stored in those registers, RCX. Actually, oh yeah, because now it's moving those into. Yeah, let's revert to the previous example because yeah, it was easier to understand here. So 1, 2, 3, 4. And then if you have more arguments, they are pushed on the stack. So you can have 6, 7. And all the additional arguments are pushed on the stack. Yeah, and I don't, and then the return value, as we said, and that's how we started about talking about that, is in the RAX register.
And I guess a couple of months ago, when you and the other the entire gang of 3 of the benchmark.net book. Also Konrad and Christoph were here.
Memory management book, right?
Yes.
Or did you also write a book about benchmarking? I don't know.
Oh, did I say benchmarking? No, my bad. I had it off by 1 error because I have both books there, the benchmarking and the pro.net memory management book. Yeah. I totally lost my trail of thought. Yes. We were mentioning about stack frames. So do we see, well, I guess we definitely see how stack is moving there. We're moving register. Are we doing something with the stack and moving some stack pointers there as well?
Yes. So yeah, that's a bit of a complex topic. Let's see on x66. Yes. So traditionally on x86 you will use the push and pop instructions to manipulate the stack. Whereas and here we set up a frame pointer. I'll go back to that. On x64, the convention is a bit different, and so you have the function that immediately bump the stack pointer with how much stack is going to need, plus some extra that is defined by the calling convention. Basically, you are I don't remember the details, but you are required to use as much stack as you need to save all the command registers. That's why even if I remove those extra values, so I stop using the stack, and you see it still increases it by 28 in hexadecimal. I don't know what is in decimal, but that's required by the calling convention.
Mm-hmm.
And that is how much space you need to save all the command registers, I would say.
Mm-hmm.
And so once you've done that, in x64, traditionally you directly reference the address on the stack instead of using the push and pop instructions. And my understanding is that it just makes the life easier for the debuggers. Because basically you set the RSP register at the beginning, and then it's easier for the debugger to find the value of your arguments on the stack.
Mm-hmm.
I don't know the full theory on it, but that's basically the gist of what's happening.
Mm-hmm.
But for that, I prefer x66 because here it's more obvious what's happening. Here you have two. So on x86, sorry, all the arguments are pushed on the stack. You don't use registers for argument passing. Mm-hmm. So here you see 2 pushes for each argument because we are using 64 bits values, but we are in 32 bits, so we need 2.
Yes. Mm-hmm.
And so for this, I should have prepared a demo because it would have been really interesting. Maybe we can circle back to it later. Yeah, let's come back to this later,
mm-hmm.
if you don't mind, because I don't know how long it's going to take to set up.
and I suppose if we push too much onto that stack, eventually we get into the infamous stack overflow.
Yeah, exactly. The OS sets a guard page on the stack. Basically, it's a bunch of an area of memory. If you try to write to it, it raises an exception at the OS level, and then it gets converted into a stack overflow exception.
Mm-hmm.
And just for later, basically this is setting what is named a frame pointer, and it allows the debugger or even the runtime to build the stack trace later. It helps creating a sort of linked list inside of the stack, and then the debugger knows how to work it, and then it knows which part of the stack belongs to what function. But we can come back to this later. Yeah.
Now it's all about the registers for like locals. Now, if we were using the arguments of the M method,
Yeah.
what would we see?
Well, we just read them from the register. Sharp-Lavix
Yeah.
really needs to be fixed. So what do we have here? Actually, I should do this. Yeah, there we go. So that's again the JIT being smart. So basically here we are calling console.writeLine with the value B. So B was in the RDX register because it's a second argument. And so first we need to move it to RCX. Whereas if I call console.writeLine A, the JIT knows that A is already in the RCX register, and so it doesn't touch it at all. And so, yes, we can talk about that. So what's happening when we call the function? We get this thing, we move it into the RAX register, and then we have this instruction. What it does is it's going to read what is stored at that location in memory and then jump to that address. So we don't jump to that address, we read what is stored there and we jump there. And this is something that is called by the JIT as the entry point of the method.
Mm-hmm.
And the idea is that this indirection allows the JIT to update the method. So basically, the first time you call the method, it hasn't been compiled yet. And so initially, it's going to point to some kind of stub. And then when you call the stub, the JIT is going to compile the method and so write the assembly code someplace in memory. Yeah, you know what? Let's bring the slides from my talk because that would be much easier to understand.
Yay. With the cats.
Yeah.
I remember because he had this tool, it's called Gummy Cat. And
Gummy
I think you
Cat.
said something, I asked you last time about the name and you said something with GC. And now
Yeah,
every time I hear GC, all I think about is Gummy Cat.
Right. Awesome. Yes. So the JIT compiles the method the first time you call it. And the way it works is, so when you call a method, as I just showed you, it gets compiled to a call instruction, and you have those square brackets, which mean that we don't jump to that address, but rather we read whatever is stored at that address. And at that address is what we call the entry point of the method. So when you start your application, at first it's going to contain the address of a stub. Inside of this stub, unfortunately, we can't show it in SharpLab, but it's going to contain this code. First, it's going to read something into the register R10. Note that R10 is not used when calling a function. If you remember, the register that we use for passing argument were RCX, RDX, R8, R9. So here the JIT on purpose use a register that cannot store the argument because it doesn't want to override the arguments of the function. It wants to preserve them.
So there is a special register that's only used for these method stubs.
It can be it's a register that is not used when calling a method.
Yeah. I see. Could be used for something else, but it's never used for. Okay.
Yeah. And so this something is called the method descriptor. This is basically the metadata of the method that we want to call. And then we have a jump to a big function that is named the pre-stub, and this is sort of the central function of the JIT. And inside of the pre-stub, the JIT is going to look at what is stored in the R10 register. So it tells it what method we are trying to call, and so it's going to compile it. It's going to emit the assembly code for that method. And that assembly code is going to be written at some address in memory. So let's say this address. And once it has done that, the JIT is going to take this address and overwrite what is written in the entry point. And then it will execute the function. And because it has updated the entry point, the next time we do this exact same method call, now we jump directly to the compile code. And so we make method calls a tiny bit more expensive because we are going through this indirection at every call. But thanks to that, the JIT is able to update the code of a function without having to synchronize with the thread, suspend the runtime, or whatever. It can just use an interlocked operation and update the address stored in the entry point. So this is what we are seeing here, basically.
I see.
This is the address of the entry point of console.writeLine. And yeah, while we are here, we can also talk about something else. So basically, the big problem with JIT compilation is that since you need to compile the method the first time you call it, is going to make that call very expensive. As a comparison, in ReSharper, since I'm dealing with ReSharper right now, more than 30% of the loading time at a startup of ReSharper is just JIT compilation. So that's very significant. And the more the JIT tries to optimize the code, and the longer it's going to take to generate. It's like when you use a compiler, when you compile in optimized mode, especially in C++, it's going to take significantly longer than if you compile in debug mode. And so the JIT has two options. It can produce low quality code, so the function will be compiled quickly, but the code inside of the function won't be optimized, and so the function itself will take more time to execute. Or it can do the opposite. It can produce high quality code, but it will take much longer to produce, and so the first call of the function will be that much longer. And so in .NET Framework, what it does, it produces high quality code. So that's why JIT compilation on .NET Framework is very, very slow.
I see. And this is then a side effect of now what ReSharper is kind of suffering from, because Visual Studio is still .NET Framework, so you can't switch as in Rider to .NET Core and have this. Basically the last 10 years of JIT improvements, right? Exactly.
And so in .NET Core, I figured out that, well, we can just do both. So in .NET Core 3, they introduced a tier JIT. And the way it works is, so as I explained the first time, you call a method is going to call the pre-stub, but this time it's going to generate a counting stub and a poorly optimized version of the method named tier 0. And the counting stub calls the method. So that's not entirely true. Sometimes the counting stub is merged with the method, and sometimes it's separate. I don't exactly know why and when it happens, but let's just say that it's always separate. And so the next time you call the function, you're going to call the counting stub, and the counting stub increments the counter internally. And then it calls the tier 0 method. And then the 13th invocation, what is going to happen is the counting stub is going to enqueue a work item to the background JIT thread. And the background JIT thread, as the name indicates, is going to compile the method in the background and generate a highly optimized version of the method named tier 1. And then once it has been generated, the JIT is going to write the address of the tier 1 method in the entry point of the method. And so the next invocations we call the tier 1 version. And so here we get the best of both worlds, because if your function is only called 1 or 2 times, then it's not worth optimizing it. And so we just produce a tier 0 version of the method, which is quick to produce. And then if you call the functions a lot of times, then the JIT realizes that you are going to want it to be optimized. It's going to be worth it. And so it's going to optimize it, but it's going to do so in the background without blocking your threads.
So is this? I just know keywords. I guess that's name dropping. Now you mentioned here, invocation 2 to 29, invocation 30. Is it always invocation 30? I guess not. And how is this related to PGO, profile guided optimizations?
Okay, so 2 things. So the 30 is the default value. You can change it with an environment variable. If you don't, then it's always going to be 30 invocations. However, there are also other conditions. For instance, there is a delayed startup where the JIT won't produce tier 1 methods. I'm not exactly sure, but I think that's because the startup is very CPU intensive, and the background JIT thread, even if it runs in background, is going to use CPU. And so the JIT just waits a bit of time before starting producing tier 1 methods.
So for a super short-lived application that lives, I don't know, a .NET tool that lives for a second, I don't need to
I think it's shorter than that. We are not talking about hundreds of milliseconds. But that's just to say that there are more conditions that decide when the tier 1 version is produced. So I don't know them all. And then you mentioned PGO. So PGO is profile guided optimization. The idea is that whenever so there are many ways to compile a method. And for instance, if you have multiple, so let's switch to Sharplab for a second. Let's say I say if a, that's so annoying, equal 1, then console.writeLine a, otherwise console.writeLine of, let's just say that. It's a bit of a weird code, but whatever. And so here we have a comparison, and depending on the result, is going to, so if RCX is equal to 1, so if RCX is different of 1, is going to jump there. Otherwise, it's just going to continue executing. And the idea is this branch is going to be faster than the other branch, which is here. Why? Because so if I call the function with a equal 1, then the CPU is going to execute all those instructions, and basically it's never going to jump. And so for the CPU predictor, it's much more friendly. Because as you might know, the CPU is trying to execute instruction ahead of time to speed up things. Whereas if a is, let's say, 0, then when we get here, we jump to line 28. So we jump here to here, then we execute this bit of code, then we jump back to 1E. So we jump back here. And so we do a few jumps, and for the CPU, it's going to be a bit slower. So the bottom line is this function is going to be slightly faster if a is 1, even though the code is equivalent in the 2 branches.
So is this a general takeaway to when writing a method and having branches, then I should write the code to assume that the if conditions are all true for the most common case, and for the less common case, then have those jumps?
Well, I first, I don't know if you if this order is going to reflect what you wrote here. I don't actually know if the JIT respects the order in which you wrote them. And regardless, you don't have to worry about that anymore, thanks to PGO. So the idea of PGO is that in the tier 0 method, the JIT is going to add a bunch of code that records the branches that were executed in the function. And when it starts compiling the tier 1 method, it's going to look at everything that's recorded, and it's going to see, oh, most of the time we take the branch where A is 0, and so it's going to invert the branches in the generated code to make it more efficient.
Oh, that's really cool. Because just for a second there, I was about to rewrite every if statement ever. No, but I don't. But this is what we got the JIT.
The JIT is doing it for you.
Yeah.
Good. Nice.
So it can do. So it can reorder branch, and it can also do optimistic devirtualization. So what is it? So optimistic devirtualization
would you mind before jumping to devirtualization?
Yeah.
I would like to come to two statements and questions. So, we talked a lot about JIT. Previously, also mentioned the AOT. So, I suppose then AOT tries to understand. Does it always emit like tier 1 most optimized code, or how does the AOT?
AOT, yeah. AOT will always, because it doesn't have a JIT compiler. So and also the compilation happens as the name indicates, ahead of time. So you have no reason not to produce the most optimized code out of the
I see. And there is also R2R, I think, ready to run.
So I haven't looked about that. Yeah, go on, sorry.
Yeah, so does ready to run pre-generate the T0 tier versions, and then later on, if I understand it correctly, then later on, so we don't have those method stubs anymore, but have immediately lowly optimized code, and then later on the JIT may tier it further.
So first to explain what R2R is it's AOT, but not as extreme as native AOT. In native AOT, you really compile your application into a native application that doesn't have a JIT, that can't load assembly, and so you have some things that you can do in .NET that you can't do in native AOT. In R2R, so ready to run, which is the modern version of Engine that existed back in .NET Framework, the idea that the assembly will contain code that is pre-JITted, but except from that, it's still a classic .NET application. And so the JIT, whenever you call a function the first time, it will try to use a code that is pre-JITted, but it isn't required to do so. And so for whatever reason, you can decide to discard it and actually recompile the function from the IL. And so you have no limitation, and you can load assembly and everything you can do in the .NET world.
So technically, I could still end up with these, with the first compilation, like similar to the pre-method stub. Or am I mixing stuff up there?
There are cases where the JIT is not going to use the pre-JITted code. I can't tell you what they are. I know that there are some situations, but I don't know them. And so to answer the question, the answer is I don't know. However, I see no reason why R2R will contain tier 0 code. It wouldn't make sense. So I'm fairly certain it's going to be tier 1 code.
Fair enough.
Cool. So I guess now it's time to devirtualize.
Yeah.
Yes. So we are really doing it out of order, but that's entirely fine. Let's say I have. interface, but doesn't really matter. And so,
I guess, are we now coming into the realms of call and call word? Am I? Oh, yeah, I see.
Mm-hmm.
Because I do read in IL call and call word and read and hear on talks devirtualization a lot. And I only know it's about performance, but that's pretty much it. I'm not quite intrigued about the implementation details.
Yeah,
and
for sure.
I guess then a follow-up question that I kind of have already is, I guess this is not only for interface. I can also imagine this is for abstract types and methods, or I guess virtual methods as well. And the follow-up question will be about sealed, but okay, we'll get there.
Yeah, so actually we don't see much here.
Could you perhaps zoom in one level more?
Yes.
Splendid.
Let's this to have less noise.
Mhm.
We don't actually see much here because everything is happening in the step. But at this point, it's enough to know. Yeah, there's my son coming in.
the co-speaker.
Co-speaker.
Yeah. Il touche à rien. Yeah, there we go. He demande what is it. He's asking what is it.
Good question.
I guess, je ne sais quoi. Does this make sense? I don't know.
Yeah, so what I was saying is we'll get into much more detail later, but if you call a method in an interface, it's going to be much slower than if you call a normal method on an object. And let's say that in callvirt, no, don't touch. I said don't touch. You always call it with my object, never with another one. Or maybe most of the time you call it with my object.
Mm-hmm.
And so during the PGO phase, the JIT is going to record what concrete implementation you are passing behind my interface.
Mm-hmm.
And then when it generates it, and then when you generate the tier 1 version of the method, it's going to use that. It's going to notice that you are always using my object, and it's going to generate some code that looks like if obj is my object. Let's say O, then O method. Otherwise. So this is optimistic devirtualization. It said that it has seen that most of the time you give my object, so it's going to say, if it's my object, I'm not going to do an interface call, I'm going to do a concrete call. Otherwise, we fall back to the interface case. And so we make the method a bit slower for interface for objects that are not my object, but we make it much faster for my object.
I see.
And since the JIT know that most of the time is this one, it's worth it.
Does this? So, well, I guess usually when you have an interface or design an interface, then it's usually not implemented by just one type. So we don't know ahead of time, especially when there is reflection or something involved, like a DI container, then, well, evaluated one time, then, yeah, compiler can figure out ahead of time what it's going called with. So it may be anything, really. Well, what I do see a lot, though, is sometimes, and actually using this, we also use this on the stream as well, to abstract a file system where we had only 2 implementations of an interface to abstract like a file system call. So for our unit tests, we then have our in-memory file system, but for real, then the system. And well, if I run the real application, I never have the the fake file system, and vice versa. Well, for the tests, I guess they don't run 30 times in one process so that the chip then kicks in. But for my live application, the chip then figures out, okay, there is only the system file system and never the fake file system. So let's devirtualize. I see. Cool.
So let's continue on that part. So first, in the situation that you mentioned, I don't know if it's already happening, but if it isn't, it will definitely happen at some point in native AOT, because we know the whole set of type. If you have an interface that is implemented by only one type, then native AOT can completely remove, in theory, could completely remove the interface. I don't know if they're doing it yet, but if they don't, I'm pretty sure that they will do it at some point. In .NET, without native AOT, there is an optimization for the case that you mentioned, but we need to take a step back to understand it. So let's see. Oh, that was the next one. That's perfect. So first, we need to understand a simplified version of how virtual cores work. So,
because toString on system.object is declared virtual, so every type in the world may override it. Yeah.
So here we have a test function that takes an object. We call object toString, and if you give an object, you will have system.object. If you give my class, you will have hello, because we have overridden the toString method. So how does test know where to find the implementation of toString to call? So let's take this example. We have abstract class with 3 abstract methods. And we have an implementation where we override each method. So we finally get to the method table. So in memory, at the beginning of the object, you will have a pointer to something that is called the method table. And inside of the method table, you will have some metadata about the type. And then you will have the address of the implementation of the virtual method in the same order as they were declared on the base class. So that's actually important. So in abstract class, we have action 1, 2, 3. So in the method table, we're going to have action 1, 2, 3. And so the idea is that they contain the address of the implementation by my class. And I have my other class. Likewise, we have the method table pointer at the beginning of the object, always at the beginning. And it points to the method table of my other class, which contains the addresses of the implementations by my other class. So in C++, that is a concept named a vtable. And once we have that, when we call, let's say, action 2 on the abstract class, what we're going to do is, from a high-level perspective, is call function number 2 from the method table. So in practice, we look at the arguments. We know that the method table is always at the beginning, so we don't even need to know the layout of the object. We don't care about how many fields it has. The method table is always at the beginning. And we fetch the method table, and we check the second function in the method table, so that's why the order is important, and then we call it. And if instead we have my other class, it's going to be the same thing, except this time we point to the method table of my other class, and likewise, we read the second address in the method table, and we jump to it. And that's how pretty much virtual cores work in .NET. What about interfaces? You may think in interface call, it's just a classic virtual call. There is no difference. And so if I have I do stuff with 2 methods, and I want to call do stuff 2, you can think, well, it's going to work the same way. So we're just going to call the second function from the method table. But with interfaces, we have one major problem, is that I can have I do other stuff, and I can have an object that implements both interfaces. And then when creating the method table, I have two possibilities. either I put the I do stuff functions first and then the I do other stuff functions. And then if I call function 2, I call the right one. Or I can put the I do other stuff functions first and then I do stuff. And then when I call function 2, I'm calling the wrong one. And so the simplistic approach that .NET is using for virtual calls doesn't work for interfaces because we have multiple inheritance for interfaces. It only works with single inheritance.
Mm-hmm.
Because if we have multiple inheritance, we can't predict in which order the methods of each interface will be laid out.
Mm-hmm.
And so we have a different mechanism. And so the method table is divided in chunks. So the notion of chunk is actually a bit complex and I don't fully understand it, so I'm not going to try to explain it. But the idea is that it's a child vtable. And so you have a child vtable for I do stuff, and you have a child vtable for I do other stuff. And you have also a chunk for virtual methods that is at a predefined offset. I'm saying that it is a bit complex because you also can have multiple chunks for the same interface. So I don't fully understand when that happens. And so now that we have that, if we want to call a method, let's say on I do other stuff, what we can do is look into the method tables and iterate over each chunk to find the one that belongs to I do other stuff. And when we have it, then it becomes a classic virtual call where we call the right method from that child vtable. However, if we have to do that at every call, it's going to be very expensive. If at every call we have to go to the method table, iterate over each chunk to find the right one, and then do the virtual call.
Mm-hmm.
So .NET has made an optimization which is called virtual stub dispatch. That's quite the name. And so the idea is that, let's say we have this code, and the first time we call it with an instance of my class. So this is actually important. When we get to the method call in the interface, we are going to call the pre-stub. At this point, you are a JIT expert. And the pre-stub is going to generate a lookup stub. Okay? And then it's going to call the lookup stub. And the lookup stub is going to generate two things. So now, first is going to resolve. I went a bit ahead. First, the lookup step is going to do the naive algorithm that I told you is going to iterate over the chunks of the method table to find the right one, and then find the address of the method we want to call. After finding the address, it's going to generate a dispatch stub, which is hard-coded with the address that was resolved, and then a resolve stub. And then the next times you call it, you're going to call the dispatch stub, and the dispatch stub is going to check, do we have an instance of my class again? If so, we directly call the address that I have hard-coded. Otherwise, I fall back to the resolve stub, and then the resolve stub is going to iterate about over the chunks to find the right one, but it's also going to add the result to a dictionary that is basically a cache. And so the next time it's going to look into the dictionary to avoid doing the full algorithm every time. And so the bottom line is that .NET is optimized for the cases where you have only one implementation of an interface, so which is exactly the case that you described with the file system. And so if you have only one, then it's going to go through the dispatch stub and use a hard-coded address, and it's going to be significantly faster.
But if I have like IEnumerable, there's like every collection is IEnumerable, so
then you are going
implementations.
So then you are going to go through the resolve stub, and you are going to have a dictionary lookup every time, which is going to be a bit slower. Also, there is some logic. If the dispatch stub has failed 100 times, then .NET is going to remove it, and is going to directly call the resolve stub.
What does it mean if the dispatch stub fails.
So basically, the dispatch stubs look if you have an instance of my class. And then if you have an instance of something else than my class, it follows back to the resolve stub. And if the resolve stub is called more than 100 times, then the resolve stub is going to remove the dispatch stub.
Oh, because
then .NET is going to conclude that you have multiple interface implementation of the interfaces, and so this optimization doesn't make sense.
Yes, I see.
And so it's going to de-optimize it, basically. And so I benchmarked it. And so the baseline is a concrete call. Virtual calls is barely slower than the concrete calls case. I think that's because, as I shown, even concrete calls go through an end direction, going through the entry point of the JIT. And so that's why I assume that virtual isn't much more expensive, because all calls are indirect anymore. Anyway. Interface monomorphic is a case where you have only one implementation of the interface. So you can see that it's 25% slower than a normal call. And then polymorphic is when you have multiple implementations of the interface. And so you don't go through the lookup stub, you go through the resolve stub, and now you are 80% slower than a concrete call. So that's significant, but we are talking about 1 nanosecond, so don't panic.
Well, so now if, from the example of the overridden toString, if I guess this works the same if I then have this type further derived and have maybe the next derived type doesn't, but the derived type now overrides toString again. Basically, then the same logic applied to check.
Yeah.
Find the actual type, and then its method table, and then invoke the method. If I'm getting that right.
Yeah, that's funny that you mentioned that, because I had this in the previous version of the talk, and then I had to remove it because it didn't fit in 1 hour.
So we get like bonus content.
Yeah, but I was wondering if I have it here, but I don't remember where. This doesn't matter. But the idea is that if I have another class that inherits from my class and overrides just action 2, for instance, is going to have its own method table with action 1 that belongs to my class, action 3 that belongs to my class, and then action 2 that belongs to the child function. To the child class, sorry.
So the method, I think now I get it. So the method table of every type knows if it overrides something from the base or doesn't.
In the method table, you are going to have in that part of the method table, you are going to have only virtual functions. You don't have.
Oh, that's different. So if I have a non-virtual, so non-virtual nor abstract, then it's not in that part of the method table.
Exactly. Because if your call is not virtual, then the JIT compiler knows exactly what type you are using. And so it can, it can directly, it doesn't have to go through the method table to call the function. It can directly put the address.
So these aren't non-virtual, non-abstract methods are not in the method table?
So they are in the method table.
They are.
But they are in a different part of the method table, and they are not used for the call. They are still present for stuff like reflection and so on, but they are not used for the actual method call.
So is now what we saw in IL at the beginning, when a method is invoked, we either have call or call word. Is this not a difference? When we have call, we basically invoke the address directly, but if we have a call word, then there is some stubbing or dispatching going on?
Not quite.
Not quite. Okay.
Because Colvert only exists at the IL level. So when we compile, Col and Colvert don't exist anymore. And so
So Colvert on IL only means that this method could be
exactly
further derived, or is an interface method that needs to be implemented somewhere.
Exactly. And there are a few subtleties. For instance, when you have a Colvert, then there are also a null check that is automatically inserted to make sure that your instance is not null. Whereas if you have a normal call, you don't have a null check. But yeah, overall, it's just a hint for the JIT compiler. So actually, I don't know what happens if at the IL level you use a call to call a virtual functions. Well, then I guess it's going to be compiled to a direct call. And so if you override the method in the child, it's still going to call the parent. I assume that's what's going to happen. It's very theoretical because you don't have control over that. C# always emits a call virt instruction.
I see. Okay. So is this for every instance method, even if it's a... So do I see the call only on static methods?
Actually, we could try it. Yeah, sorry, I'm thinking out loud. Okay, let's you nerd snipe me, so let's try it. All right, so here I have a helper. So what is this helper is doing? It takes the name of a function, and then it uses reflection to find the function. So it's a get method with a bunch of flags to be sure that I find them all. I look for the one with the right name, and then I call method handle, and get function pointer. So the idea that it's going to return me the address of the entry point of the method. So then what I can do is let's void call me. For instance, I can say var get method, something like that, and then thank you, and then we call query. So here I get the address, so it's an input. I cast it to a function pointer, and then I call it.
Okay, this is I seen this in some C# notes that this is now possible, but I don't. Can you? Wow, delegate star generic void. So that's a function pointer to a void method.
Very similar to delegates, but without type safety, which is why I use them here. So here the compiler doesn't let me write, for instance, int void. So here that will be a function that takes an int argument and return nothing.
So
actually,
that's
the compiler is letting me.
So that's quite similar to a func, basically. Do I get it right? To the system.
Oh func. Yeah, okay. That's because I'm skipping. Yes, exactly. No, not a func, an action. Here it's an action of int.
Yes.
Yeah, because normally you wouldn't use this helper. Normally, what you would do is var call me equal. Normally, you would do this. Why does it work? Because it's not static. There we go. Normally, you would do this with a function pointer. You would use this syntax. And here, the compiler has some type safety. So if I do that, the compiler says, no, this function has no argument. But what I could do is I can cast my function pointer to input. And once I do that, I don't have any type safety anymore. So here, if I do this,
now we can cheat. Or
now we
lie,
can
actually. Yes.
Yeah.
And so to avoid having to write this every time to satisfy the compiler, that's why I'm using the helper that directly returns the address. And so I skip the middleman. So just to make my code shorter. And so with delegate, you always have type safety. You can't cheat like that. If you cast a delegate is an object. And so if you cast it to object, it's still the same delegate and it still has the same type safety. The same way that if you cast something to object, then to another type, you get an exception.
Right. But with an int pointer, it could be, there is no inheritance in int pointers.
Yeah. So exactly. That's where I'm going. So what we can do is, so to be clear, I'm not sure what's going to happen.
Nice.
I can have my abstract class, virtual void call me. And here we say console.writeLine base class. It's not actually abstract, so I'm going to call it base class. Otherwise, it's confusing. And then, thank you. Thank you. All right. So obviously, if I create new derived class, if I call obj.permy, then obviously it's going to write to display derived class. So let's. Why? Oh yeah, sorry, I was deploying to WSL. That's why it takes forever. All right, there we go. Okay, so now, this is compiling to a call virt instruction. Actually, if you use a very good resharper, you have the IL viewer.
Yes.
And so here you can IL. And directly here we can see the call. So here we print the object, and here we have the call virt. So now my question is, what happens if I do? So type of, well, first thing first, if I cast my object to base class, and I do call me, then it's still going to display derived class because it's still compiled to a call virt, and in C# we have no way to change that. And so my theory is that if you have a call instead of a call me, then we will see base class instead of derived class. And that's something that we might be able to test with function pointers. So I say type of base class dot, let's take this, get methods. And then, thank you. Exactly. So here I have the address of my function. And then I'm going to cast it to a function pointer, but it's an instance method, so I have to give it the reference as we get back to it, but basically because this is an instance method, it gets a hidden first argument, which is the instance of the object.
Oh.
And then I call me what on obj. So what's going to happen? And we see base class.
Base class. So we now circumvented the...
Exactly. And if you look at the IL, then you can see when you call a function pointer, so where am I calling it here? When you call a function pointer, this gets converted to, actually it's not even a call, it's a call E.
What's
call
called
I
E?
takes, call I takes basically directly an address.
Okay.
But it's going to behave the same way as a call.
So we basically changed the call word to a call, and now there is no one-time type involved. It's always the base type compile time type.
Exactly. All right.
So if I now, I guess, if I make a type sealed or a method, an virtual method sealed so that no derived types can override it further, does this have any? I guess it has to be in the chit so that derivers know I can't inherit from it or derive this method further in VS C# or Visual Basic. But is there actually an impact on the chit level?
I don't think so, but it might. I wonder if I don't think it is, but I wonder if the compiler is smart enough to convert call virt into call if your method is sealed. I don't think it is, but let's find out. Yeah, I'm sure it's not.
Because this is then what the chit compiler then optimizes and sees there is no further derivers used or something, and then generate more efficient code. Yeah.
That's so annoying. The new virtual number is. Oh, okay. So you are not even allowed to do that.
Okay.
But then what I can do is a base class, which has the method. So and here base object, and we don't override it, but we are sealed. So what happened then? So we need to find. There's too much stuff. Call virt. It's this one. Yeah, and so we still have a call virt. Yeah, doesn't change anything.
So it's nothing that Roslyn takes into consideration for optimization, but the chit later on will.
Yeah, who knows? I honestly don't know here. I can't tell you. Yeah, here everything is trivial, so everything gets optimized.
Yeah. And now, since we talked about interfaces and methods and abstracts and virtuals, is that C#8 or some C# version we got default interface implementations? Now, this may be a nasty question because I'm not sure if you dove into this areas already. Have you?
Not so partly. Not a lot. Basically,
because we now can have
not
sure if everybody knows, but we now can have implementations in interfaces. Yeah, and I guess I'm wondering how this works, how this looks like in what does I think this also required a change in the runtime, so the chit needs to be aware of it. But yeah, I guess you haven't.
Didn't dive into it yet. I can't tell you. Yeah.
I guess then we have something for a follow-up episode.
Yes, exactly.
We were also talking about. So we have a method table, and the method. Well, I guess you were alluding to another topic, but I guess I want to interject with a question. So structs basically. If this now fits, because I think this may tie into it because you mentioned this hidden argument. What I now basically begin to understand is with objects or classes with reference types, we always have this on 32-bit systems 12 bytes, and on 64 bits 24 bytes kind of overhead, and a part of that is this method table.
Yeah.
But for a struct, we don't. It's just a value type. It's just the value directly.
Yes.
We don't have this method table attached. So if we call now, how do we now call methods on a struct? And I can imagine this ties into this hidden hidden argument kind of a thing, and apparently it also exists for classes, which I never thought of.
Not quite.
Not quite.
So, so as I told you before, if you have a concrete call, then for the call itself, it's not going to use the method table. It's going to use the method table only for virtual calls. And so for structs, it doesn't make a difference because in struct, you can't have virtual or abstract method because you don't have inheritance.
Right.
And that's why you can do without the method table. And
there's just no
yes,
need for one. Yeah.
you're going to have the hidden argument. For if you call an instance method on a struct, you're going to have the hidden argument just the same. Let's say make int value console write line of value. Yes. So we don't need this anymore, and this becomes the struct. Just remember it. All right. Okay. And so what we're going to do is likewise use function pointers. So we still want call me. Okay. And so this time the function pointer is going to take a pointer to the struct. And then it doesn't have an argument. And so to call it, I can create my struct. I will give it a value, let's say 4. And then call me is going to take the address of the struct. And so here we have the 4. And so the bottom line is that just like with classes, if you call an instance method with a struct, it's going to have a pointer to the instance. And because structs are not a reference type, this time I need to use a pointer, whereas with a class I can just write the reference.
Oh, because it's a reference type, we pass the reference.
Exactly.
So it's
and
this.
I could also use ref, which is exactly the same thing, but more C# friendly. That works exactly the same way.
So every instance method secretly gets, so this is then what this is.
Exactly.
But not just explicitly passed, but implicitly. I always there is no this, but it's passed from the caller on the instance that it was called on.
So basically, when you write that, it gets compiled into the equivalent of this, basically. And so whenever you use this, you are referencing this argument, but this is all implicit. In some languages like Python, this is explicit. When you declare an instance method in Python, you put this argument in the method.
And so, but every method is kind of, so a method doesn't magically have access to the field of its type, but then to the instance that it was called on. Hence the instance. Okay, I think I always had a wrong view on this. Okay. And if it's a class, then this is called by reference, and if it's a struct, then this is called by, no, wait a minute, because did I say this wrong? So it's always called by reference, because I get from reference type I get a reference, but from a value type I still get, well, I get a pointer or a ref to it. But now what about read-onliness? Because I can make a struct or fields read-only. Because wait a minute, I now totally may mix stuff up. So I definitely get a mutable reference to the structs method.
Yes.
I can also make methods on structs read-only.
Yes.
Does this have any JIT impact or any impact on that, so that I now get a read-only reference to it? Or is it just a C# feature that's preventing me from doing any mutations if it was marked as read-only?
So it has an impact, but not where you think.
Of course not.
Would have been too easy.
Yeah.
It's not going to make an impact here. Actually, no. If I write the whole struct read-only, it has no impact because the compiler will take care of it. What I was thinking about is, let's switch back to this. Let's say I have a struct, my struct, which has a field. Yeah, actually, yeah, I was thinking about something else. So here, my struct is not read-only, but I give it to my method using the in keyword, which is, so in is a read-only reference. So here I'm not allowed to mutate opt dot value equal 4. Here the compilation says you can't do that. It's an in, you are not allowed to. But then what happens if I have public void do something? And here I do something. Here it got inline, so that's boring. There we go. It's going to be a bit hard to understand here. Yeah, never mind. Yeah, exactly. So here, if I pass my struct and I call the method, then basically we are. So I'm not going to explain the whole assembly code, but basically we are just calling the method on the struct. That's all we do. If we use in, then here the JIT compiler has a problem in that we say that we are not allowed to modify the struct, but the JIT doesn't know how to check if do something is going to modify the struct or not, to mutate it. And so what it's going to do is, it's a bit hard to read, but basically it's making a copy of the struct, and it's calling do something on the copy of the struct.
The defensive copy. I read mysteries about it.
Actually, if I do pure, this could not be found. Then why did you autocomplete it? Never mind. I was just wondering if there was a way to. So normally the way is to just write the struct as read-only, and then the JIT sees that the struct is read-only, and so the compiler has already verified that there is no side effect, and so it's not going to do the copy.
Does this also work if you don't make the struct nor the field read-only, but only the method do something read-only? Would it then have the same effect because we only call the do something method in this call method?
Yes, it does.
And this is how we can circumvent the defensive copy. So this is what we need the read-only keyword for on structs. Do I get it right? Whenever we pass in, whenever struct by reference, in a or be in some read-only context. I guess if a struct is a field, a read-only field on a type, I can imagine it's similar. So if you're in a read-only context and we call a method, be it property or method, because I guess a property is also just a method. In this non-read-only context, then we need this defensive copy. Otherwise, we would violate the read-onliness.
Exactly. The overall recommendation is never use the in keyword if your struct is not read-only. This way you are sure that you are not going to have a problem. Because you are using in to speed up your code, and then you make copies without realizing it, and you are doing the exact opposite of what you are trying to do.
I think there is an analyzer for that, some struct analyzer that I think flags exactly that. If a struct is in a read-only context and you call a member that is not read-only, then you get a warning for potential defensive copy, and I think it's the defensive copy analyzer or something. But I'm just remembering some stuff now, and now it makes sense. This is amazing.
And so we can go back to the arguments, unless you have another question on read-only. Because I still want to address the teaser that I did at the very beginning, which is
yeah.
how are big structs passed to a method? So the idea is we take it step by step. So yes, let's clear all of that. So we get a pointer to call me, yes, and then we cast it to a function pointer, and we call it. Okay, and first we call it. Let's say it takes an object. Actually, we're not going to see anything. So yeah, let's say it takes a long. And we just display the value. So if I call it, so let's say long val, yeah, thank you. So if I call that, then obviously it's going to display 42 in the console. Nothing extraordinary here. Now let's say that it takes not a long, but a reference to a long. And I haven't changed. The actual prototype of the method. I'm cheating. And so now, because we are passing the long by reference instead of by value, now we get the address of the long. Because the function is expecting by value, but we are actually passing it by reference. So far, that's somewhat expected. So now
somewhat, I suppose. No, I'm actually not sure if I got that right. So yeah, we have a pointer to the method, but we expected this to be passed by ref.
Yeah,
no, we expect the argument to be passed, but it isn't. Now we get the address to it.
Exactly. Basically, here the method expects that the register is going to contain the value of the method. But instead, it contains the address, not of the method, of the variable. But instead, it contains the address.
Yes, I see.
Just quickly. And if you could please generate a constructor. Thank you. All right. So now, let's say that it takes my struct. And so here, my struct is 4 longs. And so it doesn't fit in a register. And so here, I give an instance of my struct.
So the size of a register, is this depending on the architecture? Is it 32 bytes, 32-bit system, byte bits, and 64 bits and 64-bit systems? Or processes, yeah.
Exactly. And so now I call it, so it's going to display 1, 2, 3, 4. And the idea is because the register is not big enough to store the struct. Actually, maybe we can see it in SharpLab. I have too many applications. So here, this is my struct. And here I have my function that takes my struct. And I lost no line. We're going to need it at some point. Okay. And then I'm going to call it. We don't have a to something, we don't care. Okay. Actually, I'm going to return the first value of the struct.
Mm-hmm.
There we go. All right, and so here I'm going to var value equal new my struct. Or we call okay. And so here, my struct. So we are supposed to store the first argument in the RCX register, but the struct is too big for that.
Mm-hmm.
And so if you look inside of the method, you can see that so RAX is the return value.
Wait, now
RCX is the
at
first
the
argument.
call Lee, right? Aren't we looking at the call method, or am I now mixing something up?
No, I'm
No.
looking at the curly.
Oh, okay. No,
Here.
I was wrong.
Yeah.
Okay.
Yeah. We see that we dereference what is in RCX,
Mm-hmm.
and then we return that value. And so the bottom line that here, if instead of my struct, I wrote ref my struct, or I wrote the pointer, that's the same thing,
Mm-hmm.
and I call value. Okay. Au revoir. It works the same way. So just to show what happened here, I did func1 and func2.
Mm-hmm.
So I'm calling the same function, but in one case I pass my struct by reference, and in the other case I pass it by value. And in both cases, it works perfectly. And the reason it does is because if you have a struct that is bigger than the register, the struct is automatically passed by reference.
If it's not.
And to make it safe, because in .NET, structs are supposed to be passed by value.
Mm-hmm.
So to make it safe, the compiler makes a copy of the struct before the method call, and then pass a reference to the copy. And so it behaves exactly as if the struct was passed by value, even though it was actually passed by reference.
But we do get the defensive copy here again to not violate
So
the behavior, because suddenly my struct, if I have a struct that is within size of a register, I copy it by value, so any mutations in this method aren't visible by the caller, but suddenly the size goes larger. Now suddenly I see them. That would be kind of weird. So hence, again, the defensive copy. Now, I read somewhere in, I guess, a Stephen Tope blog post about value type or struct promotion, where the JIT somehow sees through what is used, as we only use the long, if I got that right, and then only passes the long and not the rest, or something like that. Can you elaborate on that? Because I'd only read it, and it's just a keyword that I'm throwing out. Is this related?
So sorry, I wasn't listening to you. Sorry, because I just realized that.
Oh.
My example was bad, because in my example there was actually no copy, because I eventually tripped a JIT optimization. So before, my function was that. And here we are actually just creating the struct, and we are calling the function. So we are not making a copy. Why are we not making a copy? Because the JIT realized that after this point, we are not using the struct anymore. And so we don't care if it gets mutated or not.
Oh, okay.
But then if I change to return the original struct, then now we have a copy.
Now we have to.
Well, actually, here it's another optimization, because the JIT is actually constructed twice. So that's it.
So not copying just because we created in this method, so we can't just create it again.
Yeah, but if I received it from the caller, then it will make a copy. So now we have a copy.
Is this what a copy is? VM morph?
Yeah, that's a vectorization instruction to copy the. And if I didn't return it, then we are not making a copy, and we are actually just pathing through the value that we received to the callee, because we are assuming that the caller did the proper the copy before us.
Mm-hmm. I see. Cool. So there's defensive copies everywhere to ensure that regardless of the optimization, because if we would pass a big struct by value, this is quite expensive. Passing it by ref is an optimization, but still we need to fulfill the immutability
it's
contract.
More than optimization is required, because you can't pass it by value because the register is not big enough.
Oh, it's not even possible. Right. Yes, I see. Mm-hmm.
And now I'm ready to listen to you. Yeah, sorry, go on.
Yeah.
So, no, go ahead.
Yeah, I said I'm just ready to listen to your question again.
Because somewhere I read about value type promotion or struct promotion, where have you encountered that yet?
What do you mean by promotion?
I'm not sure. Again, I guess I only know half a truth, and I'm definitely mixing it up with something else, as I usually do. But something like that, not the entire struct is passed, but only the field that is used of it. But I may be mixing it up with something.
That could happen if the struct is only used inside of the method. But from a method to another, that I don't see how that would be possible.
Okay.
Because the JIT doesn't see inside of the other methods.
It doesn't. Mm-hmm. So unless it gets inlined, but if it's not, this is why we do it. If it's not inlined, I don't know. It could be anything, because it could be a virtual method that that needs to be dispatched first. I see. Mm-hmm.
Yeah.
Speaking of could be anything. I was wondering, because we were talking about structs a lot, but if I have a method that should work for any kind of type, like structs or classes or whatever, and I'd make it generic, what would that entail? I guess under the hood.
How would you do that? By using object?
Yeah, potentially.
Because if you use object, then the struct is going to be boxed, which basically means that it's going to be converted into an object. So moved on the heap, having a method table and everywhere, and suddenly you start passing it by reference because it has become an object.
Yeah, so that's bad, I guess, right? We always hated boxing.
We always do.
From most perspective, yes. I don't know if that answered your question or not.
Yeah, no, I suppose so. Makes sense.
And if we go back to the topic of the arguments, we have the same problem for the return value, because we need to store the return value in a register. So what happens if we want to return a large struct? So you might think we just make a copy of the struct and we return a reference to the copy.
No, but what if the struct is created in that stack and the stack frame gets popped? Now the struct is gone. I can't pass it by reference.
Yes, that's a good case. But even if that's actually a very good point. But there is another reason why it wouldn't work, and the other reason is here. So the idea is I call the method, so it gets compiled to a call instruction, and the call instruction push the return address on top of on the stack, so that the return then will pop it and we jump to it. And so in the function, if we make a copy of the return value on the stack, we are going to push it after the return address. And so when we get to the ret instruction, we are going to pop the struct instead of the return address, and the program is going to crash. So that's yet another reason why this can't work.
Mm-hmm. Mm-hmm.
And so the way it works in practice is, let's see, here. So now we say that we're still going to take a value, but we're going to return my struct. All right. So I create my function pointer. So it takes a long, it returns a my struct. And so bar results equal _1, say 42. And then we're going to display the results. Just to make sure that it works. So so 42 and 1, 2, 3, 4. All right. And so the way it works is that the compiler rewrites your code, and it adds a few things. So first it returns the return value by reference because it doesn't fit in a register. And then it adds a hidden first argument, which is a pointer to what is called a return buffer, which is basically a location in memory that is big enough to store the struct.
Mm-hmm.
And so then before calling the function, we are going to reserve some space on the stack to store the struct.
Mm-hmm.
And then we're going to call function, and we give it the pointer to return buffer, sorry. The return buffer. And then my other normal argument is just a hidden argument that is inserted at the beginning. And then it returns by reference the results, which I can then display. And so here, if I call it, you can see that it works because this is what's happening implicitly when I call the function that returns a large string. Create a return buffer, give it as the first argument, and then return the address of the struct.
Mm-hmm.
This reminds me a lot of out arguments, like the dictionary try get value.
Actually, that's a very
related.
Good point. Yeah, that's very similar. If you have an out method, then the caller reserves the place, reserves the inner space on the stack, and then gives a pointer to the function, and then the function is going to allocate the out argument inside of that space through that pointer. So that's very similar. Yeah. And just to demonstrate, I'm going to do the opposite. Call it to buffer. And now I say buffer equal or so here I completely changed my function to take a pointer to a buffer, allocate the result in it, and then return the buffer. And so I can do the opposite now, which is I take the address of call me to, and I declare it as a function that just takes a long and return a my struct. And then when I call it, it just works as expected. Because basically, those two signatures are equivalent. When you compile, the compiler transforms this into this.
Because we pass the... Oh, yes. So we have the buffer as an input, but also,
Exactly. I'm not actually sure why we have to return the buffer, even though it was given as an input. So the caller already has it, but this is required by the calling convention. So the calling convention explicitly says that you have to return the buffer and the same buffer that was given to you. You are not allowed to return something else.
Because I guess so. It can't just become void now.
Yeah,
so
but
don't we pass
I mean,
the reference? Yeah.
I can't return a reference to another struct from elsewhere. It has to be the same thing that was given to the function.
Now, okay, so we have. I guess we pointed this out on the stream, like every other stream, every other episode, we point out the significant difference between value types and reference types. What about unconstrained generics when it can be either, depending on what I call it with? If I don't constrain it with class or don't constrain it to struct.
Yeah. So whenever you have a generic that takes a value type, so just to demonstrate, let's see for my T. So if I call my func of int, this is going to be JIT compiled, and you are going to have somewhere in your process, in your memory, a my func of int. If I call my func of long, it's going to be JIT compiled, and you're going to call a different method in memory that was compiled with different bytecode. But then if I call my func of object, my func of string, my func of string, or any reference type, then all of them are going to call the same function in memory. So basically, generic functions are shared for reference types, but not for value types.
Because for reference types, they always take something that is castable to object without being boxed, or is it because the size is always 32 or 64 bit, but with a struct it could be any size really?
Pretty much, yeah. The idea, the reason why they do this is because they could, basically, but they couldn't do that for the structs.
Because structs may have different sizes.
Structs may have different sizes, and even if they had the same size, there are no virtual calls in structs. There are only concrete calls. So actually, that wouldn't be a problem, would it? Would it be a problem? That would be a problem. Yeah, that would require the struct to be boxed. Yeah. Basically, if I write where C is my interface state, in my interface, yeah, whatever I did it is. If I call my func with a struct that implements this interface, that the struct won't be boxed. The reason why it won't be boxed, and so it doesn't need a method table, is precisely because you are going to have a my func that is emitted specially for that struct, and so we can devirtualize the call. But if we wanted to share it, then we would have to keep the virtual call, and so we would have to box the structs to make it possible to have a method table.
Not sure if I got that right. If we share it, so if we would share the implementation, if we have
exactly.
I see. So every struct, if we have constraint, but if we were not generic and just take an IMA interface as an argument, now we would have boxing because there is no generic specialization going on. But with generics, we can have struct-based optimizations and avoiding the boxing. And we like to avoid boxing.
Yes, we do.
So I guess this is in general, I guess also, since if we just have generic of T that's totally unconstrained, we basically, if it's a class, then we know it's just an object. We can only do what an object is. So there is, I guess this is why we can, and if I get that right, and every reference type can be cast to object without being boxed or something. So I guess this is why they can share an implementation. Do I get that right?
I lost you at value type can be cast to object without being boxed.
So no, I don't mind value type, but any reference type, like a stream. We can cast a stream to object, a string to object without being boxed. So but we are unconstrained. We don't have any generic constraints, so we only know it. We can only call methods off of object here.
Yeah, exactly.
So I guess the common denominator is object. Yeah, I see.
Yeah, implicitly yeah, exactly.
Earlier in the stream, we got a post. Now I hope I find it again about read-only span. Do I find it again?
Yeah.
Actually, I find two things. I find read-only span, and I find params, which, well, I guess up until recently were always an array, but now can also be like any what's the attribute again? Collection builder attributed type. Anyway, I took a look at your slides and I saw something that I've never seen before.
Really? Oh,
yeah. I've never seen var args. So would you mind building up to that and explaining? I've never seen that before.
Yeah. So as you said, a function can take its value, and then it looks like my func has multiple arguments. But as you can imagine, that's not actually true. And if you look at the low-level C#, actually the compiler inserts creation of an array or a span or whatever.
We always have heap allocations with that involved.
You don't necessarily have heap invocation because I could have a read-only span.
Right. Then
and then it's going to be allocated on the stack. But the idea that the function has one, I need to compile. The function has one argument. We don't see it because
highly optimized.
Yes, stuff is happening. I don't even know what.
We see the call. There was the call I again. Underscore call I.
That's my leftover from here. Yeah.
I see.
So anyway, the bottom line is the method has always one argument. It's just a syntactic sugar. However, what you can do is arrays.
This looks well, I don't want to say wrong, but it looks very uncommon.
And then I can call it. And here the method really has a variable number of arguments, and I can pass any type I want. And it's very hard to access those arguments. You need to create an arg iterator. Oh, thank you. And then the arg iterator gives you the number of arguments. And then you can iterate. Yeah, no, you don't care. And then you can iterate on the arguments, and the arg iterator gives you a type reference. Which is, so I don't actually remember what is a type reference under the hood, but it's it had to exist because of some feature that weren't supported by .NET back then. I can't even tell you, whatever. But then you can convert the type reference to an object using, I don't even remember what. Yeah, two objects. Sorry. There we go. And so now if I run it, we can see all my arguments.
Amazing. But so to come back to the boxing, that means, but the value types, they are now boxed.
They are boxed because of the two objects, but they are not actually boxed when passed to the function. And I'm fairly sure there must be a way to extract the type from the type reference without boxing by doing some unsafe stuff.
I see. Why is the args iterator? Why does this have get remaining count? Eva and I did a talk about how for each works under the hood and the enumerator iterator pattern. Why is this not just count? Why is this a remaining count? When I say get next argument, do I kind of use them up?
Yeah, exactly. This wouldn't be necessary. They just decided to make the API that way. But the idea that, so from the caller perspective, you are just calling the function normally, which means the first 4 arguments go in registers, and then the next arguments go on the stack. And then inside of the function, the first thing it does here, it just spills the arguments. As we say, it copies all the arguments on the stack. And once the arguments are on the stack, when I reference an argument, it just references a location on the stack. So you can think of as a collection of arguments on the stack, sort of. So in theory, there is nothing that should prevent me from going from the first argument to the fourth and then back to the second one, just as the API doesn't expose it.
I see. And you're really passing in 5 arguments there. There is no hidden array allocation or anything like that. So
there is one.
Oh.
There is one. So why is that? I'm going to switch to the talk because it would be much easier to explain. Let's see. Yeah, so here, this is what I show you. So it's reported only on Windows, even Windows ARM 64, and I don't know if it works. I haven't tested, but on Linux, you will get a runtime error. The reason is that it's a legacy feature. Initially, it was designed to be able to call variadic functions such as printf from .NET code. And the thing is, they could have limited it to pinvox, but for some reason that is beyond my understanding, they decided to also allow you to write managed functions, variadic managed functions. But there is a big problem with that, is that variadic functions are deeply unsafe. Why? Because in variadic function, it's the caller that decides the number and type of arguments. That's the point of the feature. But the callee has to trust the caller to provide the right number of arguments. What I mean by that is, at the calling convention level, variadic functions don't exist. They are ordinary functions. There isn't a specific calling convention for variadic functions. And so there is no standardized way for the caller to tell the function how many arguments they gave. And to take a concrete example, let's imagine that you personally are going to implement the printf function. So printf takes a format, then any number of arguments of any type. The only way for you to know the number, to guess the number of arguments, is to parse the format. So if the format is %d, then you are going to assume that you were given 2 integer arguments. But you could call with 1 or with 4 or with arguments of completely different type, and this would compile just fine. And as the person who implements the function, you have 0 way. It's strictly impossible to know how many arguments the caller actually gave you. And the problem is that if you are expecting 2 arguments and the caller gave you 1, then this is going to be a security vulnerability.
Oh, because I may access different. I expect now at that part of the register, at that part of the stack, to be an argument, but there is something totally different.
Exactly. And so this is not acceptable for .NET because this is a managed runtime and it has to guarantee the safety of the execution. And so they added a hidden argument. So when you use arglist as compilation, there is a hidden argument that is added that is a pointer to a VAC cookie. And VAC cookie is a struct that describes how many arguments are given to the method as well as the type. And because it's emitted by the compiler, it makes sure that it exactly reflects the argument that were actually given to the function. And that's how it guarantees the safety.
So the arg iterated and uses the cookie to get the number of actual arguments. Am I connecting the dots here correctly?
Exactly. And just to demonstrate this, so I had a demo that I wrote for the talk. So let's run it. So it's it's a semi-automated demo where I go through everything that we talk about. So large struct by reference, small struct by reference, return buffer. We've seen that, and then still return buffer. So then we saw instance method that we have.
Would you mind zooming in a little?
Argument. Oh yeah, sorry. Yeah, so we have instance method where we have the method that doesn't have an argument, and you have the actual instance method that is added. So we've already seen that. I'm going to zoom here too. And then just for fun, I call it with null. And so here we get into that situation where this.name through a null reference exception, which is not supposed to happen in real life. So that was just for fun. And then finally, we get to the var args. So here I have a var arg method that I call with all those arguments. So it's going to display them. So it's the arg count and then dump all the arguments. And then I have this. So what I'm doing is I added to my project a struct that mimics the one that is emitted by the compiler, and so that is executed by the runtime. And inside of it, what it's used to so actually I don't know what any of those do. I didn't look into it. What the function used to know what arguments it were given is a signature. So the signature is a concept that is used a lot in the runtime, but that is not it's very visible if you write a profile or stuff like that. It's just a way the prototype of a function is encoded by the runtime. So it has its binary format to encode what arguments a function has and so on. And so we need to build a signature. Fortunately, there is a helper in .NET. There is in the reflection namespace, there is a signature helper that you can use to build a signature, to encode it. So I create a signature for a var args function. I add the sentinel. So what is a sentinel? The idea is that you can mix both. You can have normal args and then the arg list. And the sentinel says the arg list starts now.
But I guess those are the same rules like with params. I can't have arguments or parameters after, only before. Yeah.
Exactly. And then I says that my function, I'm going to call my function with all those arguments. So all those long and the string in the middle. And then I encode the signature and I add it to my cookie. And then I use a function pointer to call my var arg function with all the arguments passed explicitly. And so we can see that I'm passing the first hidden arguments. And so when I call it, we can see that it still works exactly the same as when I use the arglist keyword. And just to demonstrate that it's the signature that provides the safety, here I have exactly the same code, but I commented out the last 4 arguments of the signature. And when I call the function, I still give the same number of arguments. So basically, I still give all the arguments, but I tell the function that it receives 4 less than what I actually give. And if you run the code, you can see that the function now only sees 4 arguments because the signature is saying that there are 4 arguments. And because apart from the signature, the method has no other way of knowing what arguments I gave it. Yep, that's what I wanted to show.
But there is only one method. Oh yeah, there's only one. It's not like we get an implementation of test now, depending on the amount of arguments we call it with. There's only one, and it's not dynamically
I'm cheating with the
evaluated.
function pointer. Yeah.
So this is Windows only, so I guess in the cross-platform land, it shouldn't be really used in that standard library, for example. Was this there before the params, and ever since params now this is basically deprecated? Is there any use case to use this, or is this a nice, nice history into it?
Yeah, I think there was never a use case for using arglist because it was just for inbox. But I see 0 point of making a managed function using arglist. I can't even understand why they did that. And arglist is not compatible with generics, which means when .NET Framework 2 was released, they already considered this as legacy.
Oh, I see. Okay.
So I think they immediately regretted it.
But now, language features, and I think on the .NET API team, they always say API is forever. So yeah, so the architecture and the language feature is now cool. Now we
go on.
Now we mentioned that it's quite important that we are aware of the amount of arguments, otherwise we would access stuff on the stack that was maybe not initialized to what we expect. And I guess this may now close our session in a nice way, since I also saw that segment, a bit of a deep dive into, or a bit of an exploration of the stack frame, because I can imagine I also have 1 or 7 misconceptions there as well.
So you want to go to the topic of the stack frames?
Did I say yes, please? Oh yeah, I said, what did I say? Stack trace. Yes, frames.
Yeah, so I'm going to use a presentation for that. So this is a stack, as you recognize, with some stack addresses. And so when we call functions, we're going to use a call instruction, as I explained. And whenever we do that, we are going to push the return address on the stack, so that when we get to the ret instruction, we pop it and we jump to it.
We always reserve the return. Yeah. Does this also happen for a method that is void?
Yeah, exactly. Because otherwise, the CPU doesn't know where to go back at the end of the function.
Is this why? Excuse me. Is this why? Because there is a system.void type. Is this why the system.void type exists, or is this again something else?
I think it's something else. I think system.void is mainly because for dynamic functions, you can create dynamic functions, so basically emit IL at runtime. And I think it's used for that.
To declare the return type. Okay, got it.
I think so. And so here, let's say that method 1 push a few values on the stack. We don't care why. And then call method 2, so we push the instruction pointer. And then method 3 does the same thing, and so on and so forth. And when we get at this point, if we look at the stack, we can categorize it. We can see that there is the part that belongs to method 1, the part of the stack that belongs to method 2, and the part of the stack that belongs to method 3, and so on. And those are called stack frames. So the stack frame of method 1 is a part of the stack that contains the values that are pushed by method 1. And stack frames have one very interesting property, that if you look at it, every stack frames start with the return address of that method.
Mhm.
And the reason it's interesting is that it means that if we have a way to know where each stack frames begin on the stack, then we can retrieve all their return address. And if we have all their return addresses, we can build the stack trace, which is needed.
Yeah, so is this what exceptions then emit
Exactly.
and debuggers read?
Exactly. And so how are we going to find the beginning of each stack frame? One way is, I use the focus. Yeah. One way is before each method call, and we saw it when we were in x86, is to add those instructions. So I don't know if you pay attention, but when we were looking at Sharp Lab in x86, we were seeing those instructions before the method call.
Mhm.
So what is it doing? So we are going to understand that we're going to simulate the execution. So at the beginning, we have the RBP register that has value 4. So why 4? It's just an arbitrary value. We don't care. And then RSP, that is 11. RSP is a special register. It contains the stack pointer. So if you do a push or a pop in assembly, it's going to push or pop a value at the location pointed by RSP.
Mm-hmm.
So this is a special register. And so we get there, and first instruction is push RBP. So we store the value of RBP on the stack. Normally, that would increment RSP, but here I'm not doing it because then it complicates the calculation. And then we copy RSP into RBP. So RSP is 11, so we copy 11 into RBP.
Mm-hmm.
Then we execute the code, and because we have pushed some value on the stack, RSP has changed. Now RSP is 15.
Mm-hmm.
So we push RBP, so we push 11 on the stack, and we copy RSP into RBP, so RBP becomes 15.
Mm-hmm.
All right. Then we continue. At this point, RSP is 20. We push RBP, so 15, and then we copy RSP into RBP.
Mm-hmm.
Mm-hmm.
And when we get at this point, if we look at the RBP registers, it contains an address on the stack, which contains an address on the stack, which contains an address on the stack,
Mm-hmm.
and so on and so forth. And just like that, we have created a linked list of stack frames.
Mm-hmm.
And those pointers that goes from a frame to another are called frame pointers. And once we have frame pointers, it's fairly easy to work the stack. Basically, to get the first frame, we read RIP, which contains the instruction pointer, so the address of the functions we are currently executing, and RBP, which gives us the first frame pointer. So that gives us our first frame. And then we follow the frame pointers. So we find this location on the stack, and it gives us the second frame. So we read the instruction pointer and the stack pointer. And then we follow the frame pointer that gives us another location on the stack, and we follow, and so on and so forth.
Mm-hmm.
And now we have a list of instruction pointer, and then the runtime knows what function they belongs to. So we know that this one is method 3, this one is method 2, and so on. And if you are using a debugger, you can use the symbols to do the matching. And that's how you can build the stack trace. And if you use a low-level debugger such as WinDBG, you have an artifact of that. If you look at the call stack window, you can see the columns child SP and return address, which are the two information that we find on the stack frame. And so that's how so .NET use frame pointers on every platform except x64. And x64, that's because there is a special Windows API. Basically, the location of so Windows keeps track of the location of the stack frames on the stack using a special API. I don't fully know how it works, so I can't properly explain it to you.
So
Yeah.
.NET is asking the operating system on where I am and you have to go to, basically.
Yeah. Pretty much. It's actually it's callback based. So it's like I said, I don't really know how it works, but the operating system callbacks into .NET to ask where the frames are located for a given function, and then you have to use the Windows API to work the stack. There's stuff like I think RTL in one function, for instance, that is going to unwind the stack. So
okay.
I'm not fully familiar with how the stack frames are kept track, so I can't explain it in detail.
And going back to when we push to the stack, how does the runtime know of how much space to push or to reserve? Does this happen like while the method is executed, or is there basically when we enter a method, then all of the space that this method requires reserved immediately? Which there is also a term hoisting that I have in mind, but again, I may conflate two concepts.
So it depends. On x86, which is what we, and x86 is going to work that way. We don't reserve space on the stack. It's just when you do a push instruction, it's going to push the stack pointer. On x64, as we've seen in SharpLab, the JIT pre-reserve space on the stack.
Is this what hoisting is, or do I not understand what hoisting is?
I think hoisting is, I can't answer that. I'm not sure. What is hoisting again? I don't remember. I can't tell you.
Again, we have something else for the follow-up.
Yes.
I'm wondering, I guess we went through pretty much all of it, or is there something else that is worth pointing out when it comes to methods, or last chance from the audience to ask any questions about anything methods?
I just missed one that I think is interesting. So it's back to how arguments are passed. So I have a GUID. Okay. So
that's larger than the register because it's was that 128 bits?
Exactly.
Okay.
Exactly. So here, as I explained earlier, I can do this and this, and then I can put my phone with the GUID and my phone 2 with this. And if I run it, then as I explained, those two are equivalent because the GUID is passed by reference. And so in both cases, we see the GUID. But then if I run it on Linux, so where does it work?
So you're now using the Windows subsystem for Linux to call into your.
So I can't zoom on it, so I'm just going to paste it here. Basically, we saw this. So basically, the first time we saw my GUID. Actually, I should hardcode it. So just to demonstrate, I'm going to do it again.
Oh, so that's not some random GUID, yeah.
Exactly. And so here in the console, I had that. So the first time I had the GUID that I expected. Yeah. And the second time I had some garbage. Whereas if you remember, if I run on Windows, I get the same one every time.
Twice.
And this happens because Linux is using a different calling convention. And the calling convention on Linux has a special case for values that are 128 bits. And it says if your value is 128 bits, it's actually 2 arguments. And so the GUID here is going to be split into 2 registers.
Yeah.
Instead of being passed by reference. And so now when I'm passing it by reference, then we get garbage because Linux is not expecting that.
Because we don't get two arguments, we only get one, which is not the value, but a pointer to the value. So
exactly.
It's then an address. Half of the GUID is now the address of the GUID, and the rest is whatever was on the stack at the time.
And then
Do I
it's
get
going
that right?
to be garbage.
Okay.
Yeah, exactly. And so I have my my library to write profilers, and when translating one of the interfaces, I made a mistake and I passed a GUID by value instead of passing it by reference. And because I test on Windows, I never noticed, because those two are equivalent on Windows. And then somebody tried using my library on Linux, and it crashed for them because the calling convention is different.
So I guess to tie this all up to the first question, how did you get there? So basically by trying out stuff, see it fail, and then learning of what's going on.
Yeah, basically. What gave you? Which one was it? I think it was a return. Let me think. Yeah, it was this one actually. It was this one. That started it. Or I wrote some. So I wanted to write an LLDB extension. So LLDB is a Linux debugger. I wanted to write an LLDB extension in .NET using native AOT. And I ran into an issue with this because the Linux calling convention is a mess. It's a complete mess. And it has this rule that says that 128-bit value are split into 264-bit arguments, except if that argument is a C++ object with a non-trivial copy constructor or non-trivial destructor, in which case you can't split it, and so you have to pass it by reference. Why is that? I have no clue. And just for information, the full specification of the calling convention on Linux is 127 pages, and it's filled with corner cases like that. And so I ran into this issue where so I wrote, I wanted to call a native function that expected an argument that is 128-bit. And so I mapped it to a struct in .NET. But then my struct in .NET got split into two arguments because that's what the calling convention fits, except that the native function actually expected a C++ object, and so it expected a reference to the arguments, and so it crashed. And so to understand why it crashed, I had to dig into it and discover all this, and then I went into the rabbit hole.
Wow.
So what is a non-trivial copy constructor? Is that one that is
non-empty, basically?
Non-empty. So if okay.
Non-default.
So if it's not provided by the compiler?
Yeah.
Okay. I'm trying to reactivate some C++, but it's been a while.
Awesome.
So, does this mean you actually now have to special case for Linux and understand if this object has a non-trivial copy constructor to then do the right thing, or am I misunderstanding that? So how do you solve it?
Yes, so then I had to find a way for I have it here. So actually I wanted to demonstrate that, but it's not working anymore, and I didn't take the time to understand why. But basically when I ran into that, I checked a way to tell .NET to not split the struct into two registers, but this is hard because .NET is not C++, and so in .NET you don't have these corner cases. .NET is not impacted by this corner case. And I found these very weird conditions deep into the marshalling code that say that if you declare a struct, you give it an explicit size and no fields, then is going to be considered by .NET as a complex object, and it's not going to be split.
So there is no trivial copy constructor there.
Well, in .NET, there are no copy constructor to begin with.
But it's also it's also not split by .NET.
Exactly. Why? I don't know. And in fact, yesterday evening when I was preparing for today, I tried reproducing this and I couldn't. So I assume that they changed the rule in a recent version of .NET.
Oh.
Cool.
Because I have no idea why the JIT was behaving this way to begin with. It's super weird.
Fair enough. But kind of a happy accident because it taught, I guess, all of us now a lot. So,
yep.
Awesome. Well, I don't think there are any further questions from the audience. So I guess, Kevin, thank you so much for letting us pick your brain for the last 2.5 hours. It's been an absolute pleasure. And also congratulations on your talk. I mean, we've seen the presentation. It seems really, really awesome. And if our viewers would like to see more of you, where can they do that? Do you have any upcoming talks? Or I guess your blog post is always a good place to find you, right?
So my blog post that I need to resurrect because I stopped blogging because of the preparation for the talk and then the changing job. So I just didn't have time to blog anymore.
Fair enough.
So I need to continue. I have a few things to write about. And then I have no talks until October. Then in October I will be at. So which one is first? So basically October and November I will be at Tekorama in Netherlands and Update conference in Prague. I don't know which one. I don't remember which one is in October and which one in November.
Tekorama is in October and the Update conference is in Prague. I should know because that means we will see 2 more times this year. And I'm already looking forward to it.
Awesome.
Wow.
And I will be doing this talk about the arguments. I will be doing the same talk.
Amazing. Well, Stefan, I mean, you already sort of said it kind of because you also have some upcoming talks, but not just Tekorama and Prague, Update in Prague.
Oh, yeah.
Also something a little bit closer, right?
Yeah, actually this Saturday, that's on the Microsoft Zero to Hero community. They are doing in July, the .NET July. And yeah, every Saturday there is a topic of .NET. And on Saturday, I'll be talking about null and void. So yeah, 60 minutes of nothingness. And I will definitely run out of time.
Yes. I mean, that's a must. But I love the title. Like, it's everything about nothing. Awesome. Well, thank you so much also to our viewers. Thank you for spending the evening with us. It's always a pleasure. And thanks again to Kevin. You're always just so awesome to have on the show.
Yeah, it was
really,
a
really
pleasure.
thank you. And congratulations to everything you've achieved.
Thank you.
This has been amazing. My mind was blown, I guess, 17 times tonight. And I'm looking forward to meeting you again and get it blown even further.
Yeah. Just when you want to have some fun with C# internals and just call me.
Oh, we definitely need some help because now we will get for the next episode that will be in pretty much exactly 2 weeks. So that is I haven't prepared a calendar thing.
See, we're not quite back in the I don't know the
mode
pace,
the
mode.
Yeah.
Next time.
So on the 23rd of July, again, same time, same place. We will start our journey in benchmarking Rustling components. I guess we start with source generators and then also take a look at analyzers and all of them. And sooner or later, we will mess up some method calls and some optimizations. And yeah, we'll definitely we'll be picking your brain again and we'll have our minds blown several times again.
Great. And I will just give a personal message. So now I'm working on JetBrains. and my responsibility is fixing the performance of ReSharper.
Yeah.
And so the idea that if you are a ReSharper user and there is one aspect of ReSharper performance that really annoys you, then please contact me either on social media or directly by mail, kevin.gosse@jetbrains.com. And that's very important because there are a ton of things to fix. It helped me prioritize stuff to make sure that you are happy. Because if you're happy, then my boss is happy. And then if my boss is happy, then I'm paid more. And if I'm paid more, then my wife is happy. So please give all your feedback.
It's all connected.
Yeah.
Is this ReSharper? Is this only? I'm not too sure about the ecosystem. Is this only ReSharper for Visual Studio, or is this also the ReSharper that we get via Rider?
So I'm working on the one in Visual Studio. So there are bits that are shared with Rider, but my focus is really Visual Studio.
Then I guess I'll install the ReSharper plugin for my Visual Studio again and take a look at performance-related aspects.
Yeah. Thank you.
Then shout out for the community to do the same. And
Yes.
then until then, I'm still not there. Yes, there we go. We'll be back.